This is a general part of the general theory of electrons in metals. So, electrons in metals are traditionally treated as free particles. Okay, so there are two approximations: are free and independent. A large number of properties are free and independent. Many properties can be understood with this approximation. Okay, so we can understand many properties in these electronic properties of conductors using this. Free means there is no external force. Free means basically force free. And independent means there is no electron-electron interaction. Okay, this may be very surprising to some of you because you know these are charged particles and there is a Coulomb repulsion between electrons. But in many theories, we assume that such an electron-electron interaction is not important. Okay, so you have free and non-independent particles. That means these electrons are like ideal gas. The only thing that we have to worry is that these electrons are fermions. Okay, so there is quantum mechanical nature of fermions that one has to keep in mind. Importantly, what is that is very important with these fermions? That you have to keep in mind Pauli exclusion. And this Pauli exclusion is of course a consequence of antisymmetry of the wave function of these particles. And that is what gives rise to different statistics. So we have naturally an ideal gas of fermions. Electrons should be treated as an ideal gas of fermions, satisfying what is called Fermi-Dirac statistics, which we have been discussing. Now, the issue of specific heat is something like this. Suppose you have a metal. Okay, so we are interested in specific heat. Okay, and when you measure specific heat, let's say that specific heat at high temperature. Okay, let's say you're talking about specific heat at very high temperature. Then you have, let's say, metal can be now looked at as certain ions on lattice positions. Okay, ions on the lattice positions plus free electrons. Okay, suppose if you think something like let's just take an example of like sodium. So there is one valence electron, which is free electron, and then if there are n ions, and we have n electrons, because each atom will give rise to one free electron. So the n ions and n. So if you appeal to what is called equipartition theorem, okay, so we appeal to equipartition theorem, then equipartition theorem tells you that these are you have n ions, so you may have if you give some heat energy to the system, or if you supply some energy in terms of heat transfer, then these ions will undergo oscillations, and those harmonic oscillator like oscillations that we have discussed already in different models, and there is going to be some kind of a specific heat associated with that, and that is called lattice specific heat. Okay, so you have lattice contribution specific heat. Okay, which is what in classical you get what is called 3n kb. Okay, this is what turns out to be the Dulong-Pettit law. And then you have your electron specific heat, electronic specific heat, because they are also particles and they are also free to move. So this is like an ideal gas. So you may have 3/2 n kBt if they are n ideal gas particles. So total specific heat should be some of these things. And okay, if there are some interactions, etc., it may slightly deviate from this, but largely you would expect that if you do an experiment, you will get, sorry, this is energy. Okay, so specific heat, you don't have this T. Okay, so this is just what I wrote was energy, but specific heat is 3n kb here and 3/2 n kb. This is almost half of what that is specific heat is. But observation or the experiments always showed that the specific heat is only due to lattice. There seems to be no contribution due to electron. Okay, but this is puzzling because electrons are there and they are free, but yet they don't participate in thermal process. So that is very puzzling, and this is something which cannot be explained. Okay, so there is no explanation. For this result, in classical physics. Okay, so this is what is important to understand, that we require to understand this completely from quantum mechanical point of view. So there is no contribution to the electron. However, when you go to very low temperature, okay, so when you go to very low temperature, so at very low temperatures, now you may expect at very high temperature itself there is no contribution from the electrons. At low temperature, what is going to be the contribution? Because high temperature you are supposed to have larger thermal energies, and maybe excitation should become possible, and if any freezing that is taking place, it should happen as you decrease the temperature. But it turns out at very low temperature you will get a signature of the electronic specific heat. At low temperature, one observes experimentally, the specific heat will have a form like this, some gamma T plus alpha TQ. Specific heat changes with temperature in this fashion. Now, this was discovered by measuring specific heat as a function of temperature and plotting Cv by T versus T square. So if you plot Cv by T versus T square, you get a straight line. So people go to very low temperatures by using techniques called adiabatic demagnetization. And the slope of this line will give you alpha, and this y-intercept will give you gamma. So this is an indication that this is the functional form that this, and notice this is a very interesting way in which this is plotted. And if you don't plot like this, it's not possible to say that it is of this functional form, and also not possible to extract the values of gamma and alpha. Now the point is that this particular factor, or this particular part of the curve, comes because of the lattice specific heat. And as we have seen, that at very low temperature, you have Debye theory that tells you that the specific heat goes like T cube, whereas this linear specific heat is due to electronic contribution. Okay, and this is what we would like to understand, and this is done by Summerfield, Arnold Summerfield, in 1928 or something, where he had shown that this gamma T is because of the electronic specific, mainly because electrons are fermions and they obey Fermi-Dirac statistics. So this is essentially this entire theory called free electron theory of metals was put on quantum footing by Arnold Sommerfeld. Now, before we actually try to do this calculation, okay, so there is an interesting heuristic argument. Sometimes these heuristic arguments are very nice. So let me present this argument. To show that specific heat of electrons goes as T. Now this argument rests on the behavior of the Fermi-Dirac distribution function. So you can see that I think we have seen this in the last class. So let's say I have energy and the probability of the occupation of this energy, which is essentially same as the average number of particles occupying the single particle level n epsilon. And if this particular energy is the Fermi energy, which is essentially the chemical potential at 0 temperature, 0 Kelvin. So now the situation at time t temperature T equal to 0 Kelvin is like a step function, as we have seen earlier. So this is like a step function. and then it will be 0 after that. So this is the situation at t equal to 0 Kelvin. Okay. Now, for some temperature which is above 0, may not be very high, above 0, but much smaller than the Fermi temperature. Okay. So for some 0 greater than T, much less than Fermi temperature. Okay, so this particular graph gets simplified. So you will have more or less same thing here and here, but in between you will have a deviation from the 0 temperature case. Okay, so this is what this is. Now, what does this mean in physical terms is that when you give some energy, okay, so you have thermal energy. Thermal energy is of the order of kBT. This is the thermal energy. Now, this much thermal energy is available for every particle to take and go to an excited state. Now, it turns out that this thermal energy at some smaller temperature is obviously much smaller than the Fermi energy of the system. Okay, this is the thermal energy. This is much small because if you want to have thermal energy to be equal to Fermi energy, your temperature has to be Fermi temperature. But we are talking about temperatures which are much smaller than Fermi temperature. So the thermal energy available is much smaller than the Fermi energy. So now what happens to all these states? Okay, so let me just indicate. So these deeper states. Okay. Now what happens is that these states, that is electrons in these states deeper levels cannot get thermally excited. Because of Pauli exclusion. Because if you take something like this, you add kT, it will come here. But then it cannot go to that level because that level is not empty. And Pauli will not allow another fellow to occupy the same energy level. So, for most of these electrons, this thermal energy is useless. Now, which are the electrons that can take this and go to excited states are those electrons that are in the immediate vicinity of the Fermi energy. So, you can see that this particular energy, which is so let's say this particular range of energy is of the order of kB. So only those electrons which are of the order of kBt below Fermi energy can get excited. Now, since each energy level will have only one electron, so the number of electrons which which get excited will be of the order of kBt. Okay, so that means we have so energy levels that can be excited thermally okay, energy level cannot be excited. Energy levels okay, I think you have to understand this. Energy levels means electrons in those energy levels. That's what I mean. Maybe I write here electrons in energy levels that can be excited thermally are just below epsilon f of the order of kB at temperature T. Okay, so the number of electrons that get thermally excited, okay, is of the order of kBt. Remember, this I am able to say because only one electron will be there for each level. And further, each of these electrons acquire an energy equal to approximately kB. So as a result, what happens? The energy of the whole system at some temperature T is going to be some energy which was there at 0 Kelvin plus there are kBt number of electrons and each of them is gaining an energy of kBt. Okay, so this is going to be kBt the square. And of course, this is an energy square. So it is customary that you always divide this by an energy EF so that dimensionally this becomes an energy. And you can have some dimensionless constant A. So I can, by means of a pure heuristic argument, I can say that the internal energy of the system at temperature T can be of this type. Now, once I understand this, or once I get this, then I can immediately say that my CV is a derivative of this U with respect to T, and this does not contribute because this is not a function of T, and this is proportional to T, because this is T square and it will be proportional to T. Okay, so yes, so this is something which is a simple argument or a heuristic argument where we are able to understand by simply understanding the nature of the what is called population details of these electrons. We are able to argue that it is like this. Okay, so now we have, so by doing a detailed calculation, we will be able to show what this A is. That's all. I think otherwise dimensionally we have got everything correctly. So by doing this analysis, or by actually calculating this Fermi-Dirac statistics, by doing the statistics, we will be able to tell you what this A is. Any question?
I was saying that Hartley took that number of electrons that get thermally excited is equivalent to kBt.
Yeah. So you're asking why should it be like that?
Yes, sir.
Okay. So this is like this because see, this is just it's a rough argument, and the argument is something like this. So the energy range, okay, energy range for electrons to get thermally excited at temperature T is something like epsilon F minus kBt to epsilon. Okay, so if your energy is within this, then it will get excited. Is that clear?
Yes, sir.
Okay. So now what I'm trying to say is that the number of energy levels is always proportional to, there will be some factors, but this will be proportional to the range of energy, correct? So in the range of energy here is kBt. Okay, so if you are imagining that you have your energy like this, and this is your epsilon F, and let's say this is your epsilon F minus kBt. Okay, so the number of energy levels between this, so the number of energy levels in this region should be proportional to this difference. There may be some proportionality constant here, but definitely it will be proportional to kBt. Okay. Now, once you say that number of levels are proportional to kBt, then the number of electrons also proportional to kBt, because every level is occupied by one electron. Okay, so number of electrons is also proportional to kBt, since each level is occupied with one electron. Okay, so even if not one electron, even if it's two electrons, it doesn't matter, because that will be absorbed in this proportionality constant. Okay, but it is not that you can have infinitely many electrons in a particular level. Then of course this argument doesn't hold good. because depending on temperature, like in boson's case, for example, once it is below some critical temperature, then there will be huge occupation of ground state. Such things never happen. So the number of electrons that can occupy a given level is 1 or 2 if we don't consider spin, or if you consider some spin S system, then 2s plus 1. So it's some finite number. So in that case also, this argument will go through, because we are now only talking in terms of some proportionality. And this proportionality is enough for me to argue that this specific heat will be proportional to heat. Is that fine?
So, sir, this argument, the number of energy levels is proportional to KBT. This is pre-established.
This is what?
It's already established earlier in. We have already established this one. Number of energy levels proportional to KBT.
Number of energy levels proportional to KBT. See, what I'm saying is there is nothing to establish here. See, when we are talking about density of states, what do? Suppose let's say that you have so many energy levels. Okay, now let's take some particular value of energy, and then you take a small window around this energy. You call this as dE. Okay, then what do we say? The number of energy levels is equal to, definitely this is proportional to dE, but then there is some kind of a proportionality which can depend on energy, and that is added. But definitely dN is proportional to dE, right? So dN is always proportional to dE. If you take a bigger window, you get more number of energy levels, and that is what I am saying. This KBT here is like dE. It is dE because temperature is small and Fermi energy is large, and we have a small window from Fermi energy T to Fermi energy minus KBT. So the number of energy levels have to be proportional to that.
Okay, sir.
Okay. Yeah. So that is the heuristic argument. Is there any other question? Sometimes I find that this kind of heuristic arguments are very useful and good things to learn, because sometimes it is very useful when you want to explain why electron specific heat goes linearly with temperature in some interval, because you will not be able to sit down and derive all those equations. You can always do a heuristic argument, which will immediately make the point. Okay, you understand the concept and you know the crux of the matter. Okay, so but we go back to our stat mech. That means now we have to do it more rigorously. So, but I want you to notice that more rigorous calculation. So will not change any of this. Okay, so more rigorous calculation. Calculation fixes this constant. Okay, so one can think of fixing this constant by an experimental data, which is what many times people do. But then whether you have a right theory or not, you will understand once you fix this constant by theory, and then it agrees with the experiment. Okay, so that is usual procedure. So let's look at Sommerfeld's theory. Okay, so what is it that we have in our Fermi-Dirac? So our the arsenal of our theory is that we have our grand canonical partition function Q as a function of ZV beta, which is equal to product over the single particle energy state 1 plus Z e to the minus beta epsilon. And of course, we have average number of particles. N is equal to sum over single particle energy levels 1 by Z inverse e to the beta epsilon plus 1. Okay, so these are our starting points. And of course, you get this one using N is equal to Z tau by 2 Z of logarithm of Q. And of course, you write and EV by KBT is equal to logarithm of Q. And eliminate Z between these two equations. To get very important what is called the equation of state, which is easily said than done because it's not very easy to get this. Now we can use our what is called the density of states. So we had our density of states. So using density of states, okay, which is given by A of epsilon is equal to V divided by 4 pi square. Okay, so you have twice m by h bar square to the power 3 by 2 into square root of E. This is the density of states for okay, so you can actually write down you can say that we're talking about electrons, so there is a factor of 2 degeneracy for each of the levels. So I put that 2 there, then I get I think V by 2 pi square into root epsilon. So I can write down this as an integral. Okay, so your N is equal to integral V by 2 pi square into, I could have written this also outside, base square into 3 by 2 into root of epsilon, the epsilon divided by Z inverse e to the beta epsilon plus 1. Okay, so we can write down beta epsilon to be some x, so that the epsilon becomes x dx over beta, and root epsilon is root of x over beta. So you have the n is equal to V by 2 pi square into twice m by h bar square to the power 3 by 2 into 1 by beta to the power 3 by 2 into integral, this limits are from 0 to infinity. 0 to infinity, you have x to the power half dx divided by Z inverse e to the x plus 1. Now you can see that this can be written as v by 2 pi square into twice m kbt by, now this h bar I can write it as h square to the power 3 by 2, and h bar is h by 2 pi. So there is something like 2 pi to the power 3 by 2 and integral 0 to infinity x to the half dx divided by z inverse e to the x plus 1. Okay, so now you can see that this particular factor, okay, this particular factor is known to you, and that is 1 by lambda cube. Okay, so this is equal to v by 2 pi square into 1 by lambda cube, and you have 2 pi, so there are 2 pi square, so there is a 2 pi here, so I have 2 pi to the v by 2. Okay, so now 2 pi to, so there will be 2 pi, 2 pi and root 2 pi here. Okay, so let us write this as 2 pi into root 2 pi, and this I can write it as 2 pi into pi. So this 2 pi and this 2 pi will cancel, and I have v by lambda cube, and this integral is as such is there, so I'm not disturbing that, into root of 2 by pi into integral 0 to infinity x to the half dx divided by z inverse e to the x plus 1. Now you can see this now let's come back to, okay, these expressions we'll come back to. So let us now define so let me now define a function which is called f nu of z, which is equal to 1 over gamma of nu into integral 0 to infinity into infinity x to the nu minus 1 dx divided by z inverse e to the x plus 1. Okay, so if you do this, now let's look at what is gamma of 3 by 2. Gamma of 3 by 2 is gamma of 1 plus half, which is equal to half into gamma of half. Okay, but gamma half is root pi, so that is root pi. Now if you look at our expression here, I have two by root pi. So this expression, if you see, this I can write it as 3 by 2 minus 1. That will be half. And I must have divide this. Pi. Yeah, so I guess this expression has, I think 4 pi square is the correct expression. Suppose if I have 4 pi square, let's look at this. Suppose if I have 4 pi square, then this can be written as 2 pi the whole square, right? And then I have, so here I have 2 pi to the power 3 by 2. So this is 2 pi 2. So 2 minus 3 by 2 is, there is a root 2 pi in the denominator. Root 2 pi in the denominator. And if I take 2, oh, I guess we had okay, I think we have to do this calculation carefully. So first let us use this as such. So I have b by 2 pi into pi. Okay, so that is this expression. Then 1 by lambda cube. And then I have 2 pi. Okay. So I think that is the problem. Because I have just put 2 pi whole to the power 3 by 2, but I have to take 2 pi square to the power 3 by 2, because it is h square to the power 3 by 2. So it is basically 2 pi square to the power 3 by 2. So I have to only take 2 pi cube. Okay, so this is not 3 by 2. Okay, so that is, once that is done, then of course you have this integral as such. Now you can see that a 2 pi will cancel with this and you get 2 pi square. That is 4 pi square. Okay, so you have 4 pi square by pi. So that means you have 4 pi. So essentially what I'm trying to do is that h cross is h by 2 pi. And h cross square is h by 2 pi the square. And then I have to take to the power 3 by 2. So I get h square here and 2 pi cube there. So I can write down. Okay. So that is one thing. And of course, this lambda cube is not 2 mkbt, but 2 pi mkbt. So that means I have to take a pi inside and then write divided by pi to the power 3 by 2 here, so that this and this will get cancelled. So that means I have an additional divided by pi to the power 3 by 2. So now you can see what happens. This is 2 square is 4 here, and there is pi square, and pi 3 by 2 plus 1 is pi by 2. So 5 by 2 minus 2 is 1 by 2. So you have something like b by lambda cube into 4 divided by pi to the power half. okay, into this integral. Now this I will write it as 2 divided by pi into a 2 here. Now this 2 you recognize is what I have put it as a degeneracy factor, and this one is your gamma 3 by 2. So essentially what I am writing here is because of this one we can say that so because of this definition we can write down this n, the average number of particles is there is a degeneracy factor which now let me call it as gv by lambda cube. Of course for electron g is equal to 2 because it is spin half particle into f 3 by 2 of z. So this is what I wanted to establish, that this is the nature. Okay, so essentially what I'm going to do is I'm going to use my density of states. So use density of states as A of epsilon is equal to g v by 4 pi square into twice m by h bar square to the power 3 by 2 into root epsilon. So this is the expression. Of course, when I did the calculation earlier, I have used g equal to 2, then I separated. So I then put it as g so that if you are trying to use this expression for, let's say, a collection of spin 3 by 2 particles, then you can use g to be 4 and so on. So this expression is generally valid for all fermions. Okay, so for electrons, G is equal to. Okay, so this is spin multiplicity factor. For spin half particles, it is 2. For spin s particles, it is 2s plus 1. So this is the expression for average number of particles in terms of this Fermi function. Okay, so this is fine. Now you can ask what happens to this this function. For example, we have so now let us look at this expression, that is PV over KT is equal to, so let's say I have GV by 4 pi square into twice m by h bar square to the power 3 by 2 into integral 0 to infinity d epsilon and square root of epsilon. This is our density of states contribution. And then I have logarithm of, okay, 1 plus z into e to the minus beta. So I have to write down this integral. Now I would like to express this also as a part of this Fermi functions. So for that, what I will do is I integrate this by parts. Okay, so integrate by parts. Okay, so integration by parts is so I'm going to use my u as square root of e and sorry, dv as square root of e d epsilon. Okay, and u as logarithm of 1 plus z e to the minus beta epsilon. Okay, so it is straightforward. You can say that v will be 2 by 3 into epsilon to the power 3 by 2. Okay, and du is 1 by 1 plus z e to the minus beta epsilon into z e to the minus beta epsilon into minus beta dx. So this is what is your d. So you can write down this 2 by 3 into epsilon to the power 3 by 2 into u, that is logarithm of 1 plus z e to the minus beta epsilon, and evaluate this from 0 to epsilon. This is the boundary term, and minus, and there is a minus sign here, and that minus will become plus. Okay, plus I have 2 by 3 into beta. Okay, so I am actually not writing these constants. Okay, so I will keep those constants outside. So beta integral 0 to infinity epsilon to the power 3 by 2. This is v, and du. du is 1 plus z e to the minus beta epsilon. Beta I have already put outside, so z into e to the minus beta epsilon dx. This whole thing into these factors. Okay, these factors are just put here. Okay, so now notice that this will be 0 because at epsilon equal to 0, because of this term, this will be 0, and at at epsilon equal to infinity, this becomes 0, and this is logarithm of 1, and hence that is 0. So this term is 0 at both 0 as well as infinity. So we have our expression for PV over KBT is equal to 2 by 3 into beta and GV by 4 pi square into twice m by h bar square to the power 3 by 2 into I have integral 0 to infinity. Now you can see if I take this to the denominator, so I will have epsilon to the power 3 by 2 d epsilon divided by, I can write this as z to the minus 1 e to the power beta epsilon plus 1. So this is how it will be like. And now you can go back, and then of course one thing you can immediately do is that there is a volume term here and a volume term here, so that get cancelled. Okay, so now you go back and do the same trick. So set x is equal to beta epsilon. Okay, so then you have 2 by 3 beta, and I have g by 4 pi square, and let me write down twice m by h square to the power 3 by 2 into 2 pi the cube. Okay, and I will have beta to the power 3 by 2 and beta to the power 3 by 2 and a beta, correct? So your epsilon to the power 3 by 2 is x by beta to the power 3 by 2, and d epsilon is dx by beta. So I have something like 1 by beta to the power 5 by 2. Okay, and then integral 0 to infinity x to the 3 by 2 dx divided by z inverse e to the x plus 1. Okay, so let me do this because if there was some difficulty in following my previous argument, I'm also going to do the same thing here so that you can follow this carefully. So I'm going to, so now look at this, look at this expression that I have beta to the power 5 by 2 as beta to the 3 by 2 into beta. So one beta will cancel with this beta here. So there is a beta here and beta to the 5 by 2 here. So this is going to be equal to 2 by 3 into g by 4 pi square into 2 pi m kbt by h square to the power 3 by 2. And I have 2 pi the whole cube. And then I have a pi to the power 3 by 2 because I have introduced this pi here. So I have pi to the power 3 by 2. And then I have this integral as such. So you can see that 2 pi cube, this is like 2 pi square. So this 4 pi square will cancel with this and I have 2 pi there. So this is equal to g by lambda cube, that is this factor, into 2 by 3 into, now I have pi 3 by 2. So 3 by 2 minus 1 is, there is a pi sitting there. So 3 by 2 minus 1 is root pi, correct? So I have 2 by root pi. Okay, so that means I have something like 4 by 3 root pi. Is that correct? Okay. 4 by 3 root pi into the same integral. Now this integral appears that it is like, so the integral is something like this, x to the power 5 by 2 minus 1 dx divided by z inverse e to the x plus 1. So you ask a question, since it looks like it is related to 5 by 2, you ask what is gamma of 5 by 2. So gamma of 5 by 2 is gamma of 1 plus 3 by 2. So which is equal to 3 by 2 into gamma of 3 by 2. So that is equal to 3 by 2 into 1 by 2, okay, into gamma of half. So that is equal to 3 by 4 into root pi. So that is precisely what I have here, 4 by 3 root pi, correct? So now this entire thing is what is written as, so we get from here a result like this, that is P by kBt is equal to G divided by lambda cube into F of pi by 2 of Z. Okay, so this is just a representation in terms of this fiber. Now, of course, the crux of the matter is that we should be able to find out what these functions are. Okay. So in terms of finding out these functions, okay, so it looks like now these properties, properties are related to these functions. Okay, so properties can be expressed in terms of these functions f nu of z for some nu greater than 3. Okay, so now that we have established in two cases, what is the pressure and number of particles, and by eliminating z between them you can get equation of state to whatever accuracy that you can do. But we ask a question that now everything relies on getting this FNE of z. So it's important to understand how to get this FNE of z. Now that depends on this one. Like for example, for small z, okay, so for small z, just like what we have done in the case of Bose-Einstein statistics, we could write this f nu of z to be equal to 1 over gamma of mu into integral 0 to infinity. I can write this as x to the nu minus 1 into z e to the minus x into 1 plus z e to the minus x to the power minus 1 dx. Okay, so I can always expand this binomially if z is small. Okay, and this is an expansion which is which you get with an alternate signs. Okay, except that everything else is same. So I'm not going to repeat this calculation. So I want you to show that this is nothing but z minus z square divided by 2 to the nu plus z cube divided by 3 to the nu minus z to the power 4 divided by 4 to the nu plus and so on. Okay, so which you can write it in a shorthand form like this. Let's say some L is equal to 1 to infinity. So let's call this as minus 1 to the power L minus 1 into z to the power L divided by L to the nu. Okay, so this is what. So if you do this integral, so I want you to do this. Please show this. This is exactly like what we have done in Bose-Einstein case. Okay, so please show this. And remember, in the Bose-Einstein case, we got everything plus, and that is what told us that in the region between 0 and 1, this g nu of z, which we called in Bose-Einstein case, is a monotonically increasing function of z. Here we cannot make that statement because you have alternate signs. But nevertheless, for small z, this is a valid. Okay, like for example, you can say if z is very small, then f nu of z will go like z for all. Okay, it doesn't matter what is your mu, but f nu of z will go like z. Okay, so this is, but if you have not that small, but then it is reasonably small, then you can use this infinite series expansion for this. Now you can ask a question that what is the range of z for this? Okay, so we can ask a question: what is the range of variation of z? In both Einstein statistics, we have found that the variation of Z is between, so note that 0 less than or equal to Z less than or equal to 1 for BE statistics. So, what is the range of variation of Z here? Now, this depends on various things. Of course, for fermions, the range is 0 less than or equal to Z, but this Z can go up to infinity. The Z can go up to infinity. Okay, so to understand this, you can see that the Fermi-Dirac statistics. Okay, so supposing if I can have a fermion introduced into the particle, okay, such that the particle will always be placed in an energy level which is more than the fermion, which means by the addition of this particle, the amount of energy that is increased for the system is it is increasing, and it increases for the system is it can be any large. Okay, so in other words, you have this Z to be equal to e to the power beta mu. So what does that mean? That means this implies that in terms of mu, you can have minus infinity less than mu less than infinity. So when mu goes to minus infinity, this Z goes to 0, and mu goes to plus infinity, this Z goes to infinity. Okay, whereas in Bose-Einstein statistics, we had minus infinity less than mu less than or equal to 0. So mu equal to 0 is the upper bound for Bose-Einstein statistics. Okay, so here you have Z can go to it can be 0 less than or equal to Z less than infinity. So it can be very large. Now in both cases, Z very close to 0, okay, is usually the classical behavior or a very high temperature behavior. Z going to very close to 0. Suppose you fix your mu and then take temperature to be very high, then your Z is of the order of e to the power 0. That means it will be of the order of 1. Okay, so if your mu is negative, then it can become very much less than 1. Okay, and mu can become any large negative, then it can go very close to 0. Okay, so this is in some sense our analysis of this fugacity for this system. Now it is important that we should also ask, so why are we worried about this? Because as you can see now that we have expressed everything in terms of these functions, okay, and so as I said that we are interested in specific heat. Okay, so let me write down what is the expression for energy, because if you know energy, then we can get specific heat. So as we have seen earlier that the internal energy Okay, so internal energy of an ideal Fermi gas, at temperature T can be written as so I can write this internal energy as integral 0 to infinity. So you have A of epsilon, this is the density of states, into epsilon into probability of this epsilon. This is what we were saying, right? It's a probability of this epsilon. So that is equal to, you have this expression that V divided by 4 pi square. Of course, there is a G sitting there, and twice M by h bar square to the power 3 by 2, and then integral 0 to infinity epsilon to the power 3 by 2 divided by z inverse e to the beta epsilon plus 1. That is your P of epsilon. P. Okay, so now you can see that you can write this in the following fashion. That is G E by 4 pi square and twice M by h square to the power 3 by 2 into 2 pi to the power 3. And I have, if I am writing this in terms of 1 by beta to the power 5 by 2 into integral 0 to infinity x to the power 5 by 2 minus 1 dx divided by z inverse e to the beta x, e to the x plus 1. Now you can see that I can write this as gv by 4 pi square into 2 pi m kbt by h square to the power 3 by 2 into 2 pi the whole cube divided by pi to the power 3 by 2 into, there is kbt I am taking inside, and there is a beta that is sitting here, into the 0 to infinity x to the 5 by 2 minus 1 dx divided by z inverse e to the x plus 1. Okay, so now you can see that this can be written as, so let me write this as u by v. Okay, so u by v is equal to g by lambda cube, and this 4 pi square I have 2 pi and 2 pi and 3 by 2 minus 1 is 1 by 2, so I have 2 by root pi into beta, sorry, 1 by beta, or it's kbt, okay, into integral 0 to infinity x to the 5 minus 1 dx divided by z inverse e to the x plus 1. Okay, so now you can see that I have to, suppose if I take 2 by 3 I multiply here, and then I multiply 2 by 3 here, then you can see that this particular factor kbt, so other than that particular factor, so what is this one? So this one is equal to looks like kBt into G by lambda cube into what? F to the power phi F pi by 2 of Z. But remember, what is G by lambda cube into F pi by 2 of Z? It is P by kBt. Correct? That's what we had this here. Okay, before we come here, we had, yeah. So look at this expression. So P by kBt is G by lambda cube into F pi by 2 of Z. So now you can see that because of that that one. So whatever I have here is kBt into P divided by kBt. So kBt cancels. So we have now shown that the pressure is 2 by 3 U by. So this is a general expression, independent of whatever temperature we are looking at. So this is quite generally true. So now you can see that. So in terms of our this expression for the internal energy, I can now write the internal energy as 3 by 2 kBt, 3 by 2 kBt into GV by lambda cube into F pi by 2 of Z. Okay, so 3 by 2 kBt into GV by lambda cube into F pi by 2 of Z. Okay, so that is what we have for this one. Now you can see that suppose let's and also note that your n is equal to GV by lambda cube into F 3 by 2 of Z. Correct? I want you to recall that this is our expression for. So I can write from here. GV by lambda cube. Suppose if I write it as n divided by F 3 by 2 of Z. Suppose if I write it and substitute it here, then I have U is equal to 3 by 2 n kBt, 3 by 2 n kBt into, I have F pi by 2 of Z divided by F 3 by 2 of Z. Okay. Now, notice that for Z very small, F nu of Z will go like Z for all nu, which means F 5 by 2 of Z is also like Z and F 3 by 2 also is like Z. So that will cancel. Okay, so this implies F 5 by 2 of Z divided by F 3 by 2 of Z is like Z over Z, and that's equal to 1. Then you get recover your classical result. So this implies your U is equal to 3 by 2 n kBt, your classical ideal gas result. Okay, so we recover classical ideal gas. Okay, so this is one expression. And you can also see that the particular so another result that you can call is suppose if you take so another result with respect to this f nu of z is that you can write down z dou by dou z of f nu of z can be written as f nu minus 1 of z. Okay, so you can prove this. So prove this. You can do it. Easy to do it with using series solution. Using series solution. That is the easiest. You can also directly do it, but you can prove this by using. This is, in some sense, a recurrence relation. It is valid for all z. Okay, so this is another result of this f news. Okay, so now this is fine, but we will be more interested in high z because that is where the quantum effects are more important. So we will be interested in asking about, so there is more interest in high z region. Okay, so we are more interested in, so as I told you that z very small is a classical region. Okay, we have shown that it is like we recover classical eigenvalues. Okay, so we will be interested in asking a question: what happens to large z? Okay, so we have to find the behavior of these functions f nu of z for large. Okay, and this is what is called the Summerfield expansion. Or Summerfield series. Okay, so I thought we will derive those results, and that's where I have actually tried to, where I have printed these results. So this series is called the Summerfield series. So here we are expressing this in terms of xi, which is taken as logarithm of z. Okay, that is why f nu of z is written as f nu of e to the z, because z is equal to e to the z. Okay, so because of that you have f nu of e to the z. So this is having an expression like this, and in terms of that one you can have a series solution like this. And in most of our calculations, if you take zero temperature calculation, you will only see this. Now, if you take high temperature calculations, you will go up to the next term. And very rarely we need to go to a third term. So we go only up to the second term. Okay, so I have these expressions written in terms of various f's. So f phi by 2 of z up to second term, because you see xi square, xi is logarithm of z. So logarithm of z to the minus 2, minus 2, minus 2. So we are keeping only up to second term. Okay, so if you are keeping up to second term, then all experimental results can be obtained. So I thought I will be able to do this, but hello, am I audible? Okay. So I thought I will be able to show this
Yes, sir.
Summerfield expansion, but I think today I will not be able to show. So let's keep these results, but we would like to understand how these results can be obtained. So we have two tasks. So get these results, and then use these results. Use these results to get expressions for mu as a function of time, u as a function of time, and cv as a function of time. Okay, so we will do this in the next class. Okay, so I will stop here, and if there are some questions, we discuss. Otherwise, we will complete this in the next.
Sir, in all these expressions, we have this variable z, that is a function of mu chemical potential. So for different metals, this mu will be different because they have different ions and different number of electrons.
Correct.
Okay, sir.
Actually, we can also see if there is time. We can show that this particular chemical potential has some relation to what is called the work function of the metal. Okay, so we can show that in some sense you can actually calculate the work function of the metal by doing statistical mechanics. Okay, I will see if I can do that calculation. Otherwise, I can show you where you can read up that calculation.
Okay, sir.
Any other question? This constant will have dimension of energy. No, this is actually a dimensionless. I hope you are asking about that constant A, which I have written earlier, because left hand side has the internal energy, and you have kBt the whole square and epsilon f. So the dimensionally that is energy. So the constant has no dimension. It's a dimensionless constant. It will be something like pi square by 4 or pi square by 6, something like that. I think this is what Anand has asked in the chat box. I hope he's there. Okay, so if there are no questions, then we can close.
Sir, I have one question, sir.
Yes, sir.
Sir, when we discussed the adsorption desorption process, we came across the partition function as summation z phi to the power n.
Correct.
Then we wrote that summation as 1 by 1 minus z phi.
Correct.
But that geometric series will converge only when the common ratio is less than 1, no, sir.
Correct.
We have to guarantee z into phi is less than 1.
Yeah.
but how do we do that?
Okay. And also we are talking about a classical kind of that means the temperature is high and
No, sir. Theoretically, I mean,
theoretically there is no problem, no, because you consider only those degrees of freedom, and then deal with those degrees of freedom. See, when I consider an electron gas, I'm considering that as a system, and I don't care whether it is interacting with ions or it is in the metal or it is in a separate box. Right? When we are doing theory, we are doing that as a standalone system. But if your objection is that doing like that is not correct, because there are certain interactions, these electrons are interacting with the lattice ions. Yes, that is correct. But this is under that approximation where I ignore all that interactions.
sir, when we can ignore that? I mean, the interactions.
Actually, honestly saying, we can ignore that whenever your results are matching with the experiments. See, finally, experiment is the judge. For example, if you are trying to look at band theory, you cannot ignore that, because if you are interested in, I think Anand also is now asking a question about semiconductors. So in semiconductors, you have this valence band, conduction band like that. Suppose if you are interested in getting those band structure, then if you consider electrons as free, then you will not get that band structure. You have to necessarily consider electrons are interacting with the lattice and the potential of interaction is periodic. Only if you consider that, then you can get bands. So, for example, if you have certain properties where that band structure is important, which is true in specific heat of semiconductors, then you will not be able to just use a free electron theory. Okay, we cannot ignore the lattice. We have to consider the electrons in the presence of lattice and then the potential which the electron sees because of the ions on the lattice. Okay, that calculation you have to do. But in metals, somehow, you know why, but somehow you can ignore that.
Sir, there also we ignore the interaction between electrons, even in semiconductors.
Yes. There also electron-electron interaction is ignored, but then you have to also consider electron-electron interaction in some other cases. For example, if you want to understand how certain phase transitions take place or some superconductivity occurs. Okay, so like that, if you have some properties where independent electron approximation has to be given up. So it is always done in a progressive manner, depending on, okay, I am getting this experimental result, so I make a model, and if my model is fine, then I say, okay, these interactions are not important. if there is another experiment tomorrow somebody comes up with and then shows that, okay, this result is not satisfied with your approximate theory, then you have to improve the approximation. So it is a kind of crosstalk between the experiment and the theory.
Sir, one more thing, sir. When you took sodium, I think initially you talked about sodium metal. So there are
I have
11.
just today's class, right?
Yes, sir. Yes, sir. 2 days class.
Okay.
So there are 11 electrons and only one electron is free. So
Yeah.
I mean, what is the reason behind that?
Because that electron is the outermost electron, and that is the unpaired electron. So when you bring in a lot of sodium atoms together to form a sodium lattice, and these electrons will be they don't belong to any particular level or any particular atom. They get delocalized. No, essentially, what I'm trying to say is that if you want technically, the answer is something like this. Okay, so let me put it this way. Okay, so let me just try to represent like this. Let's try to take a fictitious case of, let's say I have a hydrogen atom here, and there is one energy level, and there is only one electron, and there is another hydrogen atom here. This has one energy level, and there is another hydrogen atom here, which has one energy level, and so on. Let's say there are so many hydrogen atoms. Let's for an argument's sake, let's say that this is just a one-dimensional lattice. Now, when you bring them close together, so when you are considering these n atoms, each one of this energy level has the same energy. So it is like you have n degenerate levels. Okay, so each one of them has the same energy. You have n degenerate levels. Now, when you bring them together, what happens? This nucleus will see this electron, and there will be a perturbation. So when you have this lattice, okay, when they come close together and form some kind of a lattice, now this combined energy levels are going to be n energy levels, but their energy is not same. Okay, the energy is slightly different because of the perturbation. There is a difference in energy, and instead of one level, you have actually n levels with slightly different energy. So you actually call this as a band. Okay, so now what happens? These electrons are sitting in these levels, like that. Now, this one particular energy level, this one is not, you cannot say this belongs to any one of these atoms. This energy level is, this is a delocalized energy level. In some sense, that the energy of the system will decrease. Okay, so it is exactly like your delta x, delta p greater than h cross by 2. You decrease your delta p at the cost of increasing your delta x. And this is what is actually delocalization. Okay, so this electron gets delocalized in such a way that the energy of the electron decreases, and that is what you call as, in some sense, a metallic bond. So these atoms will come together. Okay, so there is a theory which I am sure you have studied. It's called tight binding model. Okay, so this talks about how this kind of a perturbation will make these individual levels to become bands. Okay, so it is like this that you have to see how these electrons get delocalized.
Sir, then sir, why that 10 electron system will form a stable core? Only one electron will remain free.
It is not like it will become a stable core. It will also make a band, but then there is a gap between that band and the next band, right? So if there is a gap, the moment you apply some electric field or some thermal energy, it will not come out of that band. Only those electrons which have energy levels available for them to get excited will get excited. When I say electrons are free, that means they are free to move. You give some small energy, they will move. Because there are energy levels which are empty. If there are no energy levels and your band is completely filled, then we call it insulator. It doesn't conduct because there is no room for the electron to move. Because sometimes you can see that suppose if you take, since I talked about a one-dimensional crystal, you can suppose you take on every one-dimensional lattice point you put a sodium atom, and let's say there are n number of sodium atoms. Then in that band you have n levels because each atom is contributing one particular level. Okay, and now you know that Pauli principle will allow only 2 electrons. So in each level you put up down up down up down. Then you have n by 2 levels fixed. Okay, but then there are other n by 2 levels that are vacant. So that means if you apply electric field or you apply thermal energy, then the electron will actually get excited and it will take energy, go to the higher state, and there is some conduction and so on. On the other hand, instead of sodium atom, if you put magnesium atom, then there are 2 electrons in magnesium atom in the outermost shell, and then you have 2n electrons, and so you put up down, and then that band is completely filled, and the next empty band will have certain forbidden energy gap, and hence you can say that a one-dimensional magnesium crystal will behave like an insulator, and one-dimensional sodium crystal will behave like a metal.
Sir, could you tell that again? I mean, that sodium and magnesium, why magnesium will become like insulator in one dimension?
Yeah, magnesium has got 3s2, right? There are 2 electrons.
Yes,
correct?
sir.
So when you have n number of magnesium atoms coming together, there are n energy levels, but each energy level can be occupied with 2 electrons, one up and down. So that way there are 2n electrons and n levels are completely occupied. And the next energy level will be, empty energy level will be a 3p band. And there will be a gap between 3s band and 3p band, and hence small energies will not be able to excite them, overcoming that forbidden gap. As a result, for small energies that you impart to the system, there will not be any conductivity.
Okay, sir.
Okay, so if there are no questions, then we will close. Oh, sorry, something was there in the chat box. Okay. Okay, then, Shruti, we'll close. Bye.
Thank you, sir.
Yeah, bye.